Hi, welcome to Temaher Tube. In our channel we will present you some concepts in civil engineering and related fields. Subscribe and stay tuned. In today's session we will go through the reinforcement design of concrete beams subjected to bending without axial load. First, a quick introduction about the material properties of concrete and steel. In the left picture you see the strain-stress relationship of concrete from a uniaxial test, that is one-directional loading. For concrete, the relationship between strain and stress is nonlinear. This means the change in strain varies for some change in stress. Since the Young's modulus, which is stress-to-strain ratio, varies, in most codes one constant Young's modulus will be defined for design purpose. In design standards, for example Euro Code and Canadian Standard, this is defined by a secant modulus, which is a line going through the origin and 40% of the maximum compressive stress FCM. During design, the strain in the extreme concrete fiber under compression should not exceed the allowable strain according to standards ECU. At this strain level the concrete starts to crush. In the right picture you see the stress-strain relationship for two different types of structural steel, namely low-carbon structural steel and high-strength steel from a uniaxial tension test. Unlike concrete, steel exhibits a linear relationship between stress and steel until the stress level reaches the yield stress, Fy. After reaching the yield stress, it will be assumed that steel behaves as plastic material with nonlinear relationship between stress and strain. In this range steel exhibits a higher amount of deformation without a significant change in stress level. Due to the alteration of the internal structure during plastification, some additional resistance will develop, which is called strain hardening. During strain hardening, steel becomes brittle and fracture occurs when the stress level reaches or passes the ultimate strength Fu. As you see in the picture, during bending the plane of bending may tilt in different angles depending upon the amount of loading or moment. The assumption in reinforcement design of beams is that the plane of bending remains plane after bending. In the ultimate limit state design, it will be assumed that the extreme concrete fiber reaches the ultimate strain level ECU, in most codes amounting to -0.0035. It will also be assumed that the steel in tension zone is yielding. In this case the strain level in the steel will be greater than or equal to yield stress, Fy, divided by the Young's modulus of steel, E. If we consider a steel with a strength of 400 megapascal, this amounts to greater than or equal to 0.002. Using similarity of triangles, the depth of the neutral axis, C, measured from the extreme fiber in compression, to effective depth ratio, D, can be calculated by dividing the strain in concrete to the sum of the strain in concrete and steel at the ultimate limit state. If the applied load or bending moment exceeds the ultimate limit resistance of the beam starts to fail. In order to have a longer duration of failure or the failure to be recognized by the users of the structure, the failure should occur in such a way that the steel yields or elongates. The crushing of the concrete in compression zone should be avoided. Design standards enforce a tension-controlled failure by limiting the depth of the neutral axis, C, to effective depth ratio, D, to be less than or equal to 80% of the strain in concrete divided by the sum of the strain in concrete and steel at the ultimate limit state. The distribution of stress in the compression zone is parabolic. This is attributed to the nonlinear behavior of the concrete. Even if the extreme fiber in compression exhibits a higher amount of strain, due to a lower value of Young's modulus, the amount of stress in this fiber is less than the fibers in the top midsection of the compression zone, which have a relatively higher amount of Young's modulus due to lower values of strain. Hence, the integration of the parabolic stress distribution is not an easy task. Codes approximate the stress block with an equivalent stress block with a stress amount of alpha 1 times Fc and height of beta 1 times c. The alpha 1 and beta 1 values can be calculated according to Canadian standard with the formulas shown here. For normal concrete with a compressive strength of 20 to 50 megapascals, alpha 1 and beta 1 can be taken as 0.8 and 0.85 respectively. In the design of singly reinforced beams, the force in compression zone of concrete will be in equilibrium with the force in tension steel. The procedure for carrying out the design of singly reinforced concrete beams can be outlined as follows. First, for ensuring tension-controlled failure, limit the depth of the neutral axis, C, to effective depth ratio, D, to be less than or equal to 80% of the strain in concrete divided by the sum of the strain in concrete and steel at the ultimate limit state. In this calculation, strain in concrete ECU will be taken as 0.0035 in most standards, and the strain in steel equals the yield strain EY, which is the yield stress Fy divided by Young's modulus E. After calculating the C value, the force in compression zone, CC, will be calculated as a multiplication of the resistance factor for concrete phi C, 0.65 in Canadian standard, alpha 1, compressive strength of concrete Fc prime, beta 1, C, and the width of beam B. Hence the force in tension steel, TS, is equal to the force in compression zone, CC. The area of steel in tension zone AS will be calculated as CC divided by the product of the resistance factor for steel phi S, 0.85 in Canadian standard, and the yield stress Fy. For the ultimate limit state, the resisting moment, MRS, of the section can be calculated by multiplying either CC or TS with the lever arm length L, which is the effective depth d minus half of beta 1 times c. If the resisting moment, MRS, is considerably higher than the applied factored bending moment, MF, reduce C until both values are equal or MRS is a little bit higher than MF. If the resisting moment, MRS, is less than the applied factored bending moment, MF, taking into consideration the maximum value of C, either steel reinforcement should be introduced in compression zone, design as doubly reinforced beam section, or the depth or width of the beam should be increased. Alternatively, the design can also be done based on estimation of the amount of tension steel AS and calculating the depth of the neutral axis C. In this procedure, the strain in the extreme compression fiber should be fixed to be equal to ECU, 0.0035, and check should be done that the strain in the tension steel has fulfilled the criteria specified by design standards for tension-controlled failure. The design approach is the same in European and the American standards with different resistance factors for concrete and steel and different load combination factors. For doubly reinforced beams, additional reinforcement, AS prime, is required in the compression zone. An equal amount of reinforcement should be added to the tension steel for equilibrium. The design procedure for doubly reinforced beams can be outlined as follows. First, consider the beam as singly reinforced beam and calculate the resisting moment, MRS, considering the maximum possible value of C, neutral axis depth. Then calculate the difference moment delta MR between the applied factored bending moment, MF, and the resisting moment, MRS, of singly reinforced section. Hence, the additional resistance comes from the moment induced by the forces in the steel and compression zone AS prime and the additional tension steel delta AS. Equate delta MR to the product of the force in the compression steel CS and the lever arm between the compression and tension steel L2, which is effective depth D minus D1, distance to mid of compression steel from the top edge of the beam. This will enable us to determine the force in compression steel CS. After determining CS, the required area of compression steel, AS prime, can be calculated as CS divided by the product of the resistance factor for steel Phi S, 0.85 in Canadian Standard, and the stress Fs prime in compression steel. The stress Fs prime in compression steel can be calculated from the product of the strain of the compression steel and the Young's modulus. The strain in the compression steel can be calculated from considering similarity of the triangles. The calculated strain should be less than or equal to the yield strain EY. The total area of tension steel can then be calculated as the sum of CS and TS divided by the product of the resistance factor for steel Phi S and the yield stress Fy. In addition to determining the required area of steel reinforcement for the ultimate limit state, bar placement requirements to satisfy crack control should be conducted for serviceability requirements. This can be achieved in European standard by limiting the crack width to be in a range of 0.15 to 0.4 millimeters. The calculation can be done directly by determining the crack width considering service loads or by approximate methods based on the size of the bar and the stress level at service load. According to Canadian Standard, this can be done by calculating Z, which is a product of Fs and cube root of dc times A. In this formula, Fs is the service stress level, which can be taken as 0.6 times the yield stress Fy. dc is the distance of the lower reinforcement bar to the bottom edge of the beam, which is concrete cover C min plus diameter of tie bar dbt and half of diameter of lower bar db. A is the area of concrete in tension zone enclosing the tension reinforcement. A can be calculated as 2 times beam height H minus effective depth D times beam width B divided by number of reinforcement bars N. For exterior exposure condition, Z should be less than 25 kN per millimeter, and for interior exposure condition, Z should be less than 30 kN per millimeter. Thank you for listening. Leave your comments, suggestions, and corrections for better contents. Stay tuned for similar content. Don't forget to like and subscribe the channel. It will compensate our effort. Temahert Tube.